This lecture is going to cover sections 4.1 through 4.3 from the text. It's not a pencast, but instead a screencast. And that's because it's mostly qualitative ideas. There aren't a lot of equations that are convenient for summarizing what's going on. And as a result, I prefer to use slides here to make it easier so that I don't need to write. The principal idea of chapter 4 is force. And a simple one-sentence definition of force is any push or pull on an object. That's how your text begins the idea of force, and I think it's a good place to begin. However, an idea of force that's half a step more sophisticated and more useful for this class is to say that all forces come from objects interacting with each other. Full stop. All forces. There's no force in the universe that originates from a single object alone. Something like the pull of gravity on us comes from an interaction that we all have with the Earth. And then forces like friction come from interacting usually with either stuff, the air or the ground that you're moving along. All forces come from objects interacting with each other. Said another way, when objects interact with each other, that interaction produces a force on each of the objects. We'll return to that idea in a moment. So a force also changes an object's energy, potentially changes an object's energy, it changes an object's momentum, and it changes an object's velocity. We'll use that idea to expand the equations that we used in chapters 9 and 10, where we had conservation of momentum and energy for isolated systems. Thinking about forces allows us to consider systems that are not isolated, that have a change in momentum or a change in energy and a change in velocity. Lastly, force is a vector. It can be represented using the bracket notation that we've been using up to this point. It has a magnitude and a direction, and forces can cancel each other in the same way that, say, momentum was able to add up to 0. Okay, so early on in the introduction of force, it's also useful to introduce Newton's first law of motion. There are many ways of phrasing this. I think the simplest is to say that objects in uniform motion require no cause or force for their motion. The colloquial or way that you may have heard earlier is an object at rest tends to stay at rest, an object in motion tends to stay in motion. This, however, I think is a little shorter and a little more precise. Objects in uniform motion don't require a force to stay in motion. An object moving will stay moving until a force acts upon it and gets it to stop. And that is a counterintuitive idea. Most people think that objects in motion need something to kind of keep them going, and that objects, if there's no force on it, will come to a rest. The reason you think that is because that's what you see with your eyes, because everything you tend to see with your eyes has friction. You tend to not observe objects without forces on them. Friction is kind of ever present. However, in a formal sense, if there is no force, that is no friction or anything else, an object will keep moving forever. Okay, so I want to start talking about applying forces to objects and thinking about it in terms of interactions. So it's not, or one of the simplest ones to think about is thinking about the moon and going around the Earth and how they interact. So the moon goes around the Earth, and the moon interacts with the Earth through the force of gravity. There's a gravitational interaction between the moon and the Earth. That gravitational interaction exerts a force on the moon, and it exerts a force on the Earth. And so I've drawn that here, and I've purposely drawn those two arrows to be of equal length. The force of the gravitational interaction on the moon and the force of the gravitational interaction on the Earth are equal to each other. It has a stronger influence on the moon because the moon has less mass, but the force is the same. Okay, another example, imagine a person jumps and then lands on the ground, and as the person lands on the ground, they're pushing on the floor with their feet, and so I've drawn that person stick figure just after landing on the ground, and then I've copied the floor and the person off to the right on this slide, and the interaction between the person's foot and the or feet and the ground results in two forces. That interaction, that contact interaction between the feet and the floor, produces two forces. One force is on the floor, and that I've indicated as a downward arrow. And then one force is on the person upward, and that's what gets the person to stop falling. That upward arrow I haven't placed exactly on the person because it kind of disappears into the stick figure. So what I'm intending you to see here is that every interaction leads to a force on both objects. So the gravitational interaction between the Earth and the Moon leads to two forces, one on the Earth, one on the Moon. The contact interaction between the person and the floor leads to two forces, one on the floor, one on the person. Okay, so there are many, many types of forces in nature. We're going to limit ourselves to mostly this list. Um, so the most important thing about this list is that it can be broken up into two categories, the first item and the rest. The first item is weight, which is comes from the gravitational interaction that all of us have because we live on the surface of the Earth. So we all interact with the Earth using gravity, and that exerts a force on us and a force on the Earth. It, on practice, doesn't really affect the Earth much at all, but it does affect us. So we call that force weight. Every other force that we're going to deal with this semester is a contact force. What I mean by that is that the two objects interacting are touching each other. So, for example, tension, that third item on the list, is a force that is associated with ropes or strings, and a rope has to be touching an object to exert a force on it. So friction and drag are forces that are either associated with objects sliding along the ground, or in which case it's touching the ground, or an object interacting with the air, and so it's touching the air. So a spring force is the force of an object trying to restore an original shape. So the idea is a spring compressed exerts a force, and there's an interaction there that we just call spring force. Normal force is not normal as in weird versus normal, but normal in the mathematical sense, which means perpendicular. If you place an object on a table, the table will deform ever so slightly, but then push on the object in a direction perpendicular to the surface. And instead of saying perpendicular, we'll use the term normal, and that interaction is a normal, or leads to a normal force. The last two items, electric and magnetic, are actually, those are, of course, deal with things that have electric charge. And so things like electricity require thinking about electric forces. But actually, we're all made of atoms. Atoms are made of electrons and protons and neutrons. And so all interactions between atoms generally tend to boil down to electric and magnetic forces. It's not at all obvious that that's true, and it took a long time to kind of figure that out. But things like spring and tension and normal and friction and drag and thrust all kind of amount to different ways that electric and magnetic forces among atoms are producing these things that we can see with our eyes. So I include that on the list just for kind of completeness, but in practice we're not going to think about those forces until next semester. Okay, we're going to stop there and discuss